So, in the study that we've been looking at for this lesson, 35 bank supervisors recommended promotion and 13 did not. Suppose the banker's decision were independent of gender. That is, it didn't really matter whether they're male or females, they were both equally likely to be promoted. So, if we conducted the experiment again with a different random assignment of files, differences in promotion rates would be based only on random fluctuation. Well, we can actually perform this randomization using other methods, and this will simulate what would have happened if the banker's decision had been independent of gender, but we had distributed the files differently. So the idea with simulated study is to see what does random chance look like. And once we know what random chance looks like, then we'll see whether our sample fits with random chance or not. And that will determine which hypothesis we go with. So we can do this with a deck of cards if you want. We have 24 red and 24 black. Typical deck of cards has 26 of both, so you could just remove 2 red and 2 black. We will use these cards to represent the 24 males and 24 females in the study. Now we'll shuffle the cards and then deal out a sample of 13 cards. The reason I said 13 is right here that there are 13 people that were not promoted. So what we have is that the 24 red and 24 black represent the male and females. We shuffle them and we want to draw those who are not promoted. You can also draw those who were promoted, but 13 is a lot easier to count to, so I'll do the 13 and then we'll do subtraction to get the rest. So let's say this was my sample. I count, I see 1, 2, 3, 4, 5, 6, 7 red cards. So I'll put 7 males were not promoted, 6 females were not promoted. And by subtraction, I find that means that 17 males and 18 females were promoted. So in this case, there were actually more females that were promoted than males. So what is the difference in the proportion rates between the red and black in the larger group? Our simulation for those promoted. The way we find it is figure out those promoted red minus those promoted black. So 17 out of 24 minus 18 out of 24 gives me a negative difference, 1/24. So in this case, positive would mean that more males were promoted than females. A negative difference would be that more females. So, and if you try it yourself, you'll likely get a different answer. And that's fine. Now, suppose we had done this 49 more times. I'll leave it to you if you want to try that. How many simulated point estimates are at least that 29.2% we got from our original sample? Well, under our simulation, we would consider a difference of at least 29.2% an event that occurs often, or would we consider a difference of at least 29.2% often, rarely, or never? Well, I look, 29.2% is right here. I see it did occur twice. There were 2 samples out of the 50, 2 simulations out of the 50 that matched my point estimate. So it's not impossible, it's not never, but it's not particularly likely either. So my simulated point estimate of negative 1/24, now that's what this blue box here is, by the way. The simulated point estimates matching 29.2% are those 2 red boxes. It occurred, you see, it happened twice out of 50, so I would say it could occur, but not very often. So rarely might be the best choice here. And while we could physically deal out cards repeatedly over and over again, generally this is something you can do very quickly with computers. Here are the results of differences from 100 simulations, where each dot represents a simulated difference between the proportions of male and female files recommended for promotion. Because we simulate differences in a way that made no distinction between men and women, this was completely by random chance, it makes sense that the differences from chance alone fall around 0 with some fluctuation for each simulation. That is, notice that the biggest bar is here 0. Most of the dots are right here, right at 0. Considering we did this completely by random chance, or the computer did it completely by random chance, it makes sense that most of the results are right around no difference. So based on this graph, again, how often would you observe a difference of at least 29.2%? Often, sometimes, rarely, or never. Well, the first thing I want to do is locate where 29.2% is, and that's here. Here's 0.2, 0.3 would be right here, so 29.2% would be here. I notice I have one dot above it, and one even more extreme. So there are two dots here that match my original sample. Out of 100, 2 out of 100 is not a very big proportion. So only 2 of the 100 simulations are equal or more extreme than the original sample. I would say that random chance rarely matches up with my sample. When we conduct formal studies, we reject the null hypothesis if the randomly selected data strongly conflicts with that hypothesis. So in the analysis we have here, we determined that there was only a 2% probability, which we'll later call this a p-value. But there's a 2% probability of obtaining at least 29.2% more males than females getting promotions by chance alone. So it's very unlikely that by chance alone we could match up with our original sample. Because this probability is so low, we are forced to conclude that the data provide evidence of gender discrimination against women by the supervisors. That is, going back here, because there are so few studies, simulations, random chance simulations that match our original sample, it's much more likely that our sample is more than just random chance. If it's more than random chance, that means discrimination. So in this case, we would have rejected the null hypothesis in favor of alternative hypothesis.